Here we have a uniform rope that is hanging vertically, means gravity is acting vertically downward, with its two ends fixed to the wall at same horizontal level as shown. And the tension at the bottommost point of this rope is given to be 90 Newton, and the mass per unit length of the rope is 4 kg per meter. So we need to find the radius of curvature of this shape at this point C. Okay, so this 30-degree means that if you draw a tangent at point P, sorry, at point C, this tangent is going to make an angle of 30-degree from the horizontal. So we need to find the radius of curvature of the shape of the rope at point C. Okay, so how do we proceed with this question? Now suppose I take a small element on this rope, a small portion of this rope, and I am measuring X from this lowest portion of the rope, right? So suppose at position X, okay, at this position X, the tension is suppose T at, what does this represent? T at position X, tension at position X. And suppose the tension is making an angle of theta at position X. So theta X means theta angle that the tension is making at position X. Similarly, at position x plus delta x, the tension is T at position x plus delta x, and the tension makes an angle of theta at position x plus delta x. So obviously the value of tension at these two ends are going to be different, and the angle that this tension vector makes with the horizontal is also going to be different, right? And obviously, if the length of this element is suppose delta S, so there will be a weight of this element. So lambda is mass per unit length into the length of this element delta S into G. So this is the weight of this element. Now, if I say since this particular elements will be in equilibrium, okay, so the net force in horizontal as well as in the vertical direction should be zero. Now, if I make the net force in horizontal to be zero at first, so you can see that the component of this tension along horizontal will be tension cos of theta. So at position x plus delta x, the component of tension along horizontal will be T at position x plus delta x cos of theta at position x plus delta x. Okay, minus of tension at position x cos of theta at position x. So this net force should be zero. So this equation tells me that the horizontal component of tension at any point on this rope is going to be a constant value, right? So T cos theta, T is the tension at any position, and if theta is the angle that the tension vector is making with the horizontal, right? So that cos theta, so T cos theta, this multiplication, this term should remain constant, and T cos theta represents the horizontal component of tension at any point. Now, at the lowest point, if you look at the FBD of this rope, at the lowest point, if you want to draw the direction of tension, that tension force will be horizontal, right? The direction of tension is always tangential to the shape of the rope. So at the lowest point, the tension will be horizontal. So I can say that since the horizontal component of tension is same at any point, and this constant T naught actually represents the tension at the lowest point of this rope. Okay. So this T naught is the lowest point tension at the lowest point of this rope. Now suppose I make the net force in the vertical direction to be zero. So you can see that the sine components will be coming in the vertical direction. So in vertically upward direction, tension at position x plus delta x into sine of this angle theta at position x minus of tension at position x sine of theta at position x. So this difference in tension is going to balance the weight of this element. Now, if I divide this function on both sides by delta x, right, and this delta x is tending to zero, I'm considering a very small element, then this is simply a definition of a derivative in the form of limits. How do we define a derivative? So you can see that there is a function t sine theta, right? This is written as a function a t sine theta, derivative of the function t sine theta with respect to x. Okay, so this is the basic definition of a differential form like dy by dx. So if delta x is tending to zero, this function actually represents d by dx of the function t sine theta. And for delta x tending to zero, delta s by delta x can be written as ds by dx. Okay, so this is our second equation. And the first equation was t cos theta equal to a constant which is let us say t naught. Now, from this first equation, if I replace the value of t, the value of t will be t naught divided by cos theta in this second equation. So we'll carry this in the next page. So see, I've replaced t equal to t naught by cos theta in this second equation. So this expression becomes d by dx of t naught into sine theta by cos theta, which will be tan theta, equal to lambda g into ds by dx. Now t naught is a constant, so we can bring this out of the derivative. And tan theta will be the slope of tangent at any point, which I can write as dy by dx. And this expression ds, you see, this is a small element of small length ds, so I can consider it approximately like a straight line. So I can make this ds into two components. I can break this ds into two components, dx and dy. And I can write ds is equal to under root of dx square plus dy square, simply Pythagoras theorem. So ds can be written as under root of dx square plus dy square and divided by this dx term. So d by dx of dy by dx, it becomes double derivative of y. So d square y by dx square equal to, I bring this t naught term in the denominator, lambda g by t naught. And this dx can be taken inside this under root. This term comes out to be 1 plus dy by dx whole square. So this is a differential equation which actually represents the shape of the rope. That shape of this hanging rope is actually not a parabola, it is called as a catenary. So this is the differential equation which represents its shape. Now, a mathematical equation for radius of curvature at any point that can be given as, if you have a equation of a curve y as a function of x, then you can find the radius of curvature at any point on that curve using this expression, that is 1 plus dy by dx square whole power 3 by 2 divided by the double derivative of y with respect to x. So in this expression, this d2y by dx square in the denominator, I am replacing it from this equation 3. So this expression radius of curvature comes out to be t naught by lambda g into 1 plus dy by dx whole square. Now remember, this t naught was the horizontal component of tension at any point, which was also equal to the tension at the lowest point of the string. And this lambda is the mass per unit length, g is gravitational constant, and g is acceleration due to gravity, and dy by dx is the slope of tangent at any point on the rope. So in the question, you can see that we were asked what was the radius of curvature at point C. So if you draw a tangent at point C, this tangent is making an angle of 30 degree from the horizontal. So dy by dx at point C is actually tan 30, which is 1 by root 3. And tension at lowest point is given to us as 90 Newton. Lambda was given as 4 kg per meter. And g is given to us as 10 meter per second square. So simply you replace these values in this given equation, in this expression for radius of curvature. T naught is 90, lambda is 4, the value of g is 10, and 1 plus dy by dx square will be 1 by 3. So this radius of curvature comes out to be 3 meters.